Good afternoon, everyone, and welcome to the second in our MyCorps Spring Webinar Series. We're really excited to have you here. My name is Jo Lattimore. I am the director of the Michigan Clean Water Corps, which is Michigan's Lake and Stream Volunteer Monitoring Program. And we're going to start out with a really quick instructions on how to participate in our webinar. All the information you need is right there on the screen, but I'll also mention that for now, we will have the chat turned off to minimize distractions, but if you have questions for our speaker today, feel free to use the Q&A button, which you will find at the bottom of your screen. Just click on that Q&A button and you will be able to type in your question for our speaker. I'll be moderating those questions and asking them of our speaker at the end of her presentation. We're again really thrilled to have you here, and when we turn on, we will turn on the chat after the presentation is over if you have comments to add or feedback for the speaker and so forth. We will also have at the end of this presentation, when you leave the Zoom, you'll be invited to provide some feedback and a very quick survey to let us know what you thought of today's presentation. Next slide, please. I want to spend a moment or two just to say a few words about the MyCorps program. MyCorps, or the Michigan Clean Water Corps, as I mentioned before, is our statewide volunteer lake and stream monitoring program. And the program has three components. The first of those is the volunteer stream monitoring program. And through the volunteer stream monitoring program, we invite organizations around the state to get involved with monitoring the health of our streams by collecting the insects that live in those streams, which are excellent indicators of the health of our streams, and also to collect data about the habitat in those streams. These stream programs are run by groups like watershed councils and conservation districts and other organizations all around the state of Michigan. So if you're interested in volunteer stream monitoring, check out our website, which we'll see in a minute, to help you connect with a local MyCorps group in your area. Next slide. Our other stream program is our volunteer stream cleanup program. Through this program, we offer grants to local municipalities to organize stream cleanups, to remove trash from our streams and rivers all over Michigan. And we actually offer a grants program to support both the stream monitoring and the stream cleanup programs. This year's grant cycle actually ends today. Today is the last day to submit grant applications for this year, but we do this every single year through support from the state of Michigan. Next slide. The other aspect of MyCorps is our cooperative lakes monitoring program for anyone who's interested in volunteering to monitor the health of our lakes and streams. Our volunteers get involved with monitoring the plant communities, both native and invasive in our lakes, like you see here in this photo, also monitoring water quality and habitat status in lakes all across Michigan. And every year, more than 300 lakes across Michigan are part of this volunteer program. And enrollment is open now through May for the volunteer monitoring program. So we're always encouraging new lakes to get involved. Next slide. If you want to learn more about MyCorps, simply go to mycorps.net, and then you'll find all the information you might be interested in about this program. We are sponsored by the Michigan Department of Environment, Great Lakes and Energy, and the program is run by MSU Extension, the Huron River Watershed Council, and Michigan Lakes and Streams Association. And we're thrilled to be able to host this series of webinars, our first ever, that has been organized and is being put on by graduate students in MSU's Department of Fisheries and Wildlife. So today I'm really excited to introduce our speaker, Janice Albers. Janice is a master's student a PhD student, in our Department of Fisheries and Wildlife, studying under Dr. Cheryl Murphy. She earned her bachelor's degree from the University of Wisconsin, Stevens Point, followed by a master's in fisheries and wildlife from the University of Missouri in Columbia. She is primarily interested in understanding human impacts on fish populations, so to implement aquatic restoration actions. So without any further ado, I'm going to hand the mic over to Janice. Welcome.
Great. Thank you, Jo, for that introduction. And thank everybody for joining our seminar series, and especially today to learn about riverine ecosystems. Today, I just wanted to share with you some of the things that I see quite often in our rivers and I think typically go unnoticed by most people. So first, I wanted to review with you the what natural flowing rivers look like and how hydrology then creates this diverse ecosystem. Then I wanted to touch on some common ways that humans have impacted rivers. And lastly, how to restore then the health of our riverine ecosystems. So I think typically when riverine ecosystems are mentioned by most folks, they tend to immediately think about the biology. And here we have invertebrates and zooplankton, and of course, my favorite, fish, and birds and amphibians, and then even the herbivores and the predators for those herbivores. But in reality, the riverine ecosystem is actually way more complex, and it includes disciplines like hydrology, hydrogeology, hydraulics, and geomorphology. And all of these disciplines tend to focus on and study how water and land interact. And in reality, biology is just one piece in this complex puzzle of nested physical and chemical processes, like the landscape processes that interact with hydrology, that then interact with the sediment and nutrient transport and cycles. And finally, this one box way down here is the biology. These interactions have also been described in the rivers functions pyramid, which some of you may have heard of. So how does water create this diverse ecosystem? Well, water doesn't flow over land in a linear way, but creates meanders. And this happens because water interacts with itself in that it creates these spirals, these vortices, these water vortices as it flows over the land. Now, these vortices kind of bounce their way back and forth through this channel, where on the outside bend, they create erosion. And then on this inside bend, they create deposition. They also create a real diverse set of depths in this channel, where the outside bend is typically deeper and the inside bend is more shallow. In addition, they create these a diversity of velocities, and this dashed gray line indicates then the deepest and fastest part of this channel. This is also known as the thalweg. Now, if we look at this from a bird's eye view, from a top view, we can see then these vortices that are kind of bouncing back and forth, and they erode and deposit, erode and deposit. Now you can see sometimes these vortices on the surface of the water, and here's an example of a picture of a river that's during a high water event, but you see this line of kind of white frothy material. It's probably organic matter here down this part of the river. And what this is an interaction between these two vortices. So on the left side of this line, you have one vortice that's working this way down the river. And on the right side of the line, you have another one that's working this way. And so this is one way that we can see these vortices that are on the surface of the river. These vortices also create areas of high and low velocities that tend to sort substrate and create substrate diversity. So here on these outside bends, then you get large, hard, clean substrate, where on these inside bends tend to deposit small, soft, and muddy substrate. This sorting of substrate occurs in this cross-sectional way, but it also longitudinally, where you have low flow sand deposited in a deeper area with some high flow cobbles and boulders, but then in the more shallow areas, you have these high flow pebbles and cobbles. So there's this rearranging of substrate in these channels. In Midwestern rivers, the interaction then between the substrate and these water vortices naturally result in a river channel that contains what we call a riffle-run pool complex, which is a series of riverine habitats that repeat as you go downstream, where a pool then typically occurs on the outside bend, and it's a fairly deep habitat with diverse substrate. Runs then are typically upstream of a pool, and this is the least diverse habitat because it has uniform depth and velocities. And then upstream of the runs are riffles, and this is typically a shallow water, but it has really complex substrate and velocities. Now, I like to think of riffles as piles of rocks, and these piles of rocks are, of course, an easy place to cross the river, but if you think of them as piles of rocks here, longitudinal cross section, where you have these riffles and run pool, riffle, run pool complex. But each one of these riffles, then the water not only flows over that pile of rocks, but it flows through that pile of rocks. And when it does flow through these piles of rocks, you filter out different types of substrate and nutrients. So there's like this in-channel filtering that goes on at each riffle. In general, then you can relate increases in habitat diversity with increases in biotic diversity, just like in any ecosystem. Now, another way to think about this land-water interface is through this equilibrium analogy, typically shown with a scale or a balance, where on one side you have water resistance, and this can be created through sediment load, or say a tree falls into the channel, so you might get some in-channel obstacles, or even the meandering will create resistance against water flow. On the other side of this scale, you have water power, and there's multiple factors that influence water power, one of them being the slope of the riverbed. So if you think of a waterfall and the water that's flowing over that waterfall has a lot more power. You can also increase water power through the volume of water. So increasing the volume will increase power. And if you have a straight river channel versus a meandered one, a straight one is going to have more power behind it, the waters, because nothing's resisting that movement of water. Now, this balance can change depending on certain events. Say we had a rain event. And of course, that's going to increase the amount of water volume in that channel. So that makes this side of the scale go down, so you have more power, and that then shifts that needle over to the erosion. So during that water event or rain event, you're going to have more erosion in that channel. Or say we have a beaver that comes in and constructs a dam over that river. And so then you have more resistance, and consequently you get more deposition upstream of that dam. Now, these temporary states only last for a certain amount of time, and eventually this river channel will get back to an equilibrium between erosion and deposition. So the same amount of resistance equals the amount of power that's being generated. And this is an important concept, that river channels are always going to go back and try and get to this equilibrium between erosion and deposition. Now, lateral movement of the channel, or in other words, movement from side to side, is a natural process where when the water flows over the land. And satellite imagery has really helped tremendously in understanding this process. Here's some images from a recent study of a river in Bolivia. And so they took some satellite images from 1986 to 2018. And over this time, then they were able to see how each river meander behaved, how it moved across the land, and the different forces involved in this process. Now, it's one thing to see a two-dimensional image, and what I'd like to share is some images of these satellite images over time. So here's an example of a different river in Peru. As you can see, the floodplain is highly forested, not very many humans in this river watershed. And as you can see over time, then this river is moving laterally across the floodplain. And you see like channel crossover or cutoffs happening, and you get these oxbow lakes. There's a very large one that happens here where it cuts off, and then you get an oxbow lake. So there's a lot of lateral movement going on. The other thing I wanted to point out here is that the width of the footprint of that river is a lot wider than just where the water channel is. Here's another picture of a river in India. And again, the watershed doesn't have a whole lot of human impacts. So this river can then meander back and forth in unconstrained motion. And you can see these waveforms kind of moving, they're moving down the floodplain. And here's another meander that then gets cut off. And so these are the ways that rivers will flow naturally across the land. So now that we have a good idea of how a natural flowing river looks like, I want to, sorry about that, talk a little bit about how humans have impacted rivers. Typically, the first thing that comes to most people's minds is hydro dams, and they definitely disrupt connectivity and disrupt the hydrology of that river channel. But a thing we often forget about is that we, for many hundreds of years, have used rivers as a place to put our pollution. So we typically put it in the river, and the river conveniently moves it downstream somewhere. We also do things like dredge rivers, where we take out the sediment so that we can maintain some water depth for maybe flow or boat traffic. We also like to build around rivers, and this picture shows a nice river channel that has completely been changed over to cement. And the last two I want to talk about is channelization, which is where we go and straighten a river, and incision. Now, incision is a term that describes a river where the river bed has decreased in elevation. So I'm going to talk about a couple of these in more detail here. First, migration barriers. So in the Great Lakes watershed, we have a little over 7,000 hydro dams. Now, hydro dams are typically what people think about when they think about migration barriers, but there's another type of migration barrier, and that is road crossings. And we actually have over 250,000 of those. Now, this study in 2013 did a survey of those road crossings and found that about 64% of them were not passable by fish. So that leaves about 172,000 road crossings that are migration barriers. And when I mean migration barriers, we typically think of perch culverts. And a perch culvert is when the culvert is higher than the bed of the stream, so that in order for a fish or an invertebrate to move up past this barrier, past this road crossing, they'd have to jump up into this culvert. And native fishes are really bad at jumping. So this ends up being a impediment to their moving up through this road crossing. Another thing I want to mention is land drainage and channelization. This is pretty common in Michigan. Michigan has been doing this for at least 200 years. And so it tends to be difficult to find a river in Michigan that hasn't been impacted by this activity in some way. Actually, most Michiganders alive today don't even realize that the streams that they're seeing are a culmination of these 200 years of land modification. These pictures here kind of give you a sense of the magnitude of the impacts when water is drained from the land and creeks are channelized. So these main outlets then are field main outlets of the field drains are also known as rivers to us, but these are drainage main drains for these fields, and they have to be really deep so that they can provide a lower outlet then for the buried drains that are in the ag fields. The management of these drains are known. The management of these drains, we created then this new governance that we like to call drainage districts. And in Michigan, there are currently about 35 counties out of the 83 that have active drains that are managed by drain commissioners. That means that there's a little over 16,000 actively managed drains in Michigan. So what happens to a stream when you channelize it? So here's our reference again with the natural flowing condition where the river is moving back and forth across the floodplain, and it creates then this overland flow and underground flow of water between the channel and the floodplain and all the nutrient processing and functions that go on in the floodplain. So when you channelize a river, you obviously create a limited hydrologic connectivity. So this floodplain gets really narrow. And you disrupt then these connections with the flowing water overland into the floodplain and all the processes that go on there. In addition, a channelized stream can also create a false sense of security to those who live nearby, and consequently, then they place infrastructure in the floodplain. So another way to view this is by this cross-sectional example. So here we have a cross-section of a stream, and say it hasn't rained in a while, so we have base flow. And in this example, I want you to think about groundwater level as approximately the same as what's in the river. So in this example, say it rains, and we have an increase in the amount of water in the channel up to about bank full. And say it rains a little bit more, and then the water overflows the banks and goes off into the floodplain. Now, what happens in that same river if we've channelized it? So here's our original cross-sectional area, but we've increased it, so we've dug it deeper. So the rain event that previously allowed the water to go overland into the floodplain now is restricted to that channel and doesn't go off and over into the floodplain. In a channelized levee condition, so typically when you channelize a stream, you tend to take the spoils out from the channel and stick them on the river bank. So it's kind of a double whammy where you're increasing the bank height and decreasing the river channel depth. So overall, when you channelize the stream, you lower the water table. You also increase the water power because you're having more water in that channel because you're bringing more off the land. And this increased power that's going on in this channel, it can't move laterally anymore. So that power then tends to be focused on the river bed, and that bed tends to erode downward. This extra power also then removes habitat for fish and invertebrates, and it also creates substrates that are typically uniform in size. So back to our balance analogy, here we have our natural flowing river that's equal erosion and equal deposition. Well, with a channelized condition, you of course have increased water volume because you're bringing more off the land, and you have a straightened channel, so you don't have any resistance due to meandering. So channelized streams constantly have this more power scenario where there's more power, which equals more erosion that's going on in that channel. Now, typically this river channel would want to get back into equilibrium, but because of those high banks, it can never get there. So it's in this constant state of high power, high erosion. Some of you might be wondering about those water vortices and whether or not they continue after channelization, and sure enough, they do. However, they're confined and restrained into these two embankments. And here's an actual picture of a channelized river showing that very thing. So we have very little water in this channel, but you can see there's still a deeper area that's bouncing back and forth, a channel that's bouncing back and forth between these embankments. And that's those water vortices trying to create these meanders, but they're hitting these embankments. The other thing you notice in this picture is that the substrate is fairly uniform. We got a lot of sand and a couple pebbles. So there's not that sorting that goes on anymore in a natural river. So a little bit about incision in rivers. Incision is a term, again, that describes a river where the river bed has decreased in elevation. And as an example of channel incision, I'm going to talk about a river that many of you might have heard of. So MSU is located on the banks of the Red Cedar River. And the benefit of this long-term association between MSU and the Red Cedar River is that there's been a photographic record of changes that have occurred on the river. So the oldest picture I found of the Red Cedar River on the internet was from 1888. And here we have 9 strapping young men who are taking a dip in the river. And a couple things I want to point out in this picture. First of all, the amount of vegetation that's on the banks of the Red Cedar River. We got bushes, we got shrubs, we got small trees, lots of vegetation on the banks. The second thing I want to point out on this picture is that the slope from the cameraman to the river the men in the river, it's not very steep. And especially as it relates to that opposite bank, you can see that opposite bank's fairly steep over there. So this indicates to me that the cameraman is standing on the inside bend of the river and that the slope of the bank is fairly gradual. Now let's jump forward in time to about 1945. And one of my favorite pictures I found of the Red Cedar River, where we got these really old trees and lots of vegetation. It looks very peaceful. But again, the slope of the river is fairly gradual. The banks aren't that steep. Now let's jump ahead to 1967. And we can see here, we can see a concert going on, but in the background, we can see the river. And again, here we have a bank that's fairly steep, and that's the far side bank, but the near side bank also has some slope as well. As evidenced by this tree here, see, we can't see the root ball, and so that's lower. So that means that this edge of land kind of drops off down into the water. And finally, we get a picture from today, and we can definitely see that both the outside bank and the inside bank are fairly steep. If we compare it to 1945, it looks like back then we had about a man in height kind of river bank situation, and today we got about 2 men in height. So to me, this indicates that the channel has deepened from incision. So the base of the river, the bed of the river has gone down in elevation. In addition, the other thing I noticed in comparing these images is that the width of the water in the channel has increased over time. And this could be due to changes in climate, yes, but more likely due to the increase in drainage in runoff that's upstream in the watershed of this river. So now I want to talk a little bit about the positive things. What can we do? And I want to touch on a little bit about restoring longitudinal and lateral connectivity, restoring some aquatic habitat, and some natural water filters. Now, all of these actions essentially attempt to restore a balance of that resistance versus power, and also restore or increase these natural hydraulic, nutrient, and biological functions. So let's talk about longitudinal connectivity. Typically, removing migration barriers is one of the quote unquote easiest kind of river restoration projects you can do. Here's an example of the North Lansing Dam on the Grand River. And here we have coho and steelhead trout that come up from Lake Michigan, and they hit this dam and they can jump 6 inches, fine out of the water. So they go up the Benke fish ladder and off they go upstream. However, like I said before, the native fishes are very bad jumpers, and consequently, they can't use this Benke fish ladder. So what happens then when we take these dams out? First of all, it increases then fish access to habitat and food. So say like there might be spring spawning habitat upstream that the fish are trying to get to, or maybe really good feeding overwintering habitat downstream. Removing dams also reconnects them this physiological and hydraulic function and processes. And here's a good example down here on the lower right hand of an image of a dam removed on the St. Joseph River in Michigan. And here they replaced it with riffles. So like I said, these riffles are natural filters, so they're filtering the water. But also if you look upstream, the bank upstream is fairly shallow. So this river has access then to the floodplain and can work out into the floodplain and use those processes as well. In addition to dams, we can start trying to attack some of those 172,000 road culverts that are impeding fish movement. And you can do that by these eco-friendly culvert designs. And what they typically do, is allow sediment to pass from upstream to downstream underneath this culvert. But in addition, of course, they let the fish also move downstream to upstream and invertebrates. And lastly, they also have increased capacity to handle these high water events so that they don't act like dams and potentially get washed out. So they last longer and we don't have to replace them as often. So as a society, then we can support dam removals and road departments in these eco-friendly culvert replacements. And when I say support, I mean both socially and monetarily. Now, a little bit about restoring in-channel habitat. Now, there are many ways to restore in-channel habitat, and I wanted to mention just one today pertaining to large woody debris. So restoring and maintaining a healthy amount of large woody debris in a river channel creates habitat for fish and their food. But it also helps to keep a good balance then between that resistance and power dynamic that's going on in the channel. However, there does seem to be a lot of local pressure to remove this type of habitat. So I wanted to just mention this and make you aware that there are consequences to doing this, such as, of course, taking and decreasing fish habitat, but also changing that resistance power balance when you remove large woody debris. So I would suggest just to be cautious about this and essentially just remove enough for boat passage. So now I want to mention a little bit about natural water filters. Now, one of the difficult problems to solve in river restoration is to understand why a stream is out of balance, say either has too much erosion or too much deposition going on. So most of the time, the imbalance is due to human landscape practices. And restoration can be way more effective and widespread when humans understand their impacts and change their behavior. So these two images show a lot of erosion that happens in an agricultural landscape. And so what we can do as a community then is to support no-till farming practices and have winter cover crops, because a lot of these erosion events happen during the winter, say like last week when we had the ground was frozen, but then we get rain. So the rain can't go and percolate into the ground, but it has to flow overland into the river channel. We can also have large river riparian buffer strips that are seeded with native plants that have really deep roots. And what this does is then filter the water and remove that sediment, keep the sediment on the land before it gets to the river channel. We can also restore our upland water filters like wetlands seen here, but also in-channel filters like the riffles I mentioned earlier, but also floodplains. So here's a sequence of images that show a river in Minnesota. It has a floodplain that's really grassy. I think this is probably reed canary grass. But either way, the water gets out into the floodplain and the suspended sediment in that water starts adhering to the vegetation. And by the time it flows back into the channel, it's a lot cleaner than the original channel water. But in order for us to have these floodplain filters, we need to restore lateral connectivity. In other words, we need to allow the water from the channel to connect to the floodplain during these rain events. And an incised channelized stream definitely does not have any connections to that floodplain. And so how do you go about fixing this situation, a channelized stream? Well, removal of those levees is simple enough, but how do you elevate a riverbed? And actually, this is one of those most difficult restoration objectives is elevating a riverbed. Now, some people might think, oh, we just put the dirt back in there and be done with it. Well, we can't really do that either because it's against a lot of our pollution laws nowadays. So some of the other ideas that people have come up with include installing riffles. Now, I mentioned before riffles as filters and as piles of rocks. And so if you think of then these piles of rocks as being kind of like mini dams, then upstream of these riffles, it will elevate the riverbed just a little bit. And when you start thinking of riffles as mini dams, then you can kind of see how beaver dams would also elevate the base of the river upstream of them. And lastly, and most expensively, we could construct new shallow channels. And here's an example of that in Minnesota, where you see here we have the original channelized stream here right next to the road. Adjacent to that, what they've constructed is this meandering channel here, just like with all of its semi-natural meanders. But this channel is also a lot shallower. And so they've designed it so that it will reconnect and inundate the floodplain then every couple of years. Now, last but not least, in restoring lateral connectivity is involves thinking about parts of the land as fish habitat, something I like to call terrestrial fish habitat. And yes, I know this seems kind of strange, but to aquatic organisms, high water events can be a time of plenty where the fish can increase their feeding rate and spawn. And these areas are highly productive areas. I personally define terrestrial fish habitat as any part of the land that will at any point in time be covered by water and allow fish to access it. Now you have to imagine the land then during high water events as well as during base flow. So high water events actually construct fish habitat in both the channel and the floodplain, but only if we let it. So we need to reconnect the floodplains to the river channel and have our buildings and infrastructure located in such a way that accommodates this river's lateral movement and increased width during these high water events. So one way to minimize then these human conflicts with the rivers is to be aware of the location of our infrastructure relative to the river and how the river may interact with it. So that during these high water events, then instead of thinking of them as destruction events, we can think of them as construction events. And here's an example of that. So here's a satellite image of the Washiack River in southwestern Michigan. And this river was actually channelized a little over 100 years ago. And at least some parts of it still remain in this active drainage district. The first thing I want to point out on this image here is this construction here. And I was a little concerned about it first, but then I found out that it was where they took the dam down. So yay, dam removals. But the other thing I want to mention is these roadways. Now, from a river's perspective, roads are a lot like levees in that they restrict and confine the lateral movement of water. The other thing I wanted to point out here, and I hope some of you have noticed, all these houses that are located in the floodplain. So with the information I've presented today, I hope now you can see that these houses may be interacting with the river in the future. And as much as I love rivers and would love to live in one of these houses, I also know that it isn't a good idea for the house or the river. So thinking about rivers in both time and space will help us understand that rivers need room. And that's the main takeaway I want to present to you today, is that we need to give rivers room. And that rivers are not like lakes. We can't just plunk down a house right next to one and expect the river never to move again. So if we don't give rivers room, then it just increases these conflicts between humans and nature. And we want to work smart with nature. And preventing future conflicts is part of this equation. That way, we can also, where infrastructure and communities allow, then start restoring both the longitudinal and lateral connectivity and our natural water filters. And lastly, and most importantly, I want you to get out and experience nature so that after this seminar, when the next time you see a stream, you start to think about and appreciate all those geophysical and biological components that culminate in a very complex riverine ecosystem. And maybe even grab a snorkel or a paddle, and hopefully you'll come to appreciate what an important resource our riverine ecosystems are. And with that, I have my references, and if this thing ever goes away, my email address, in case you want to communicate.
Thank you so much, Janice. I really appreciated that overview of river ecosystems and how they work. I know I'm always fascinated by the paths that rivers take and how they kind of decide on their own where they're going to go, whether we decide that we want to build our house there or put our field there or something like that. The river kind of decides where it wants to go. And I particularly enjoyed seeing those pictures of the Red Cedar River. I did my doctorate research on the Red Cedar, so it's one of my favorite rivers in the whole world. So those historic pictures are really cool. All right, I did want to mention to all of our audience, this has been recorded today, and we will be posting the recording on the MyCore website. So give us a week or so to get that edited and up for you. And if you didn't catch everything or you wanted to share it with others, this and all of the webinars in this series are being recorded and posted on our website. And if you have questions for our speaker today, please use the Q&A button to post those into the Q&A box. I've also turned the chat on, so if you have comments or feedback, feel free to use the chat there. So Janice, I think I'll kick off some questions for you.
Sure.
All right, so first question comes from someone who says they're new to Michigan and they're curious to know if there is statewide support for dam removal projects, or does this happen in Michigan on a smaller scale?
I think there's probably just as much support as there are in other Midwestern states. I think the biggest limitation to dam removal is monetary support. So that tends to be the hurdle, but there are quite, as an example that I showed, they're popping up and they're becoming more frequent. So that's always good. That's always good.
Absolutely. And I'll also mention from my own experience, the Michigan DNR is one source of funding for some dam removal projects. They have some fish habitat grant programs that I know many communities in Michigan have taken advantage of to do that. And they also offer a lot of technical guidance on how to do it well. And many other organizations in Michigan do that as well. They do very much. And thanks for mentioning that.
I would say that there always seems to be more requests than funding available. So.
Absolutely. All right, next question. The questioner says, well, I might have missed this, but what causes those vortices to develop in the stream itself?
Yeah, those vortices are very interesting, and they occur from the interaction of the water with itself. It's hard to explain. There's a lot of physics involved. But even if you had, say, a straight cement square channel, those vortices are still going to be happening in there. And it's just how the molecules in the water react with one another, and they just naturally form. So.
All right, cool. Yeah, those vortices tend to happen in lakes too, which is something that's really interesting with the wave motion. And that's why you see, like you showed, the lines of debris on the surface of a stream. The same thing happens in lakes and causes sometimes foam lines.
I didn't know that one.
Yeah, foam lines will happen on lakes and people will see that. All right, next question. And I think you mentioned a little bit about this, but if you wanted to expand on it a little bit, as a property owner, if a tree falls or branches fall into the stream by my house, should I just leave all that in place? Should I remove part of it? Like, what should I do with that kind of debris?
So if I was lucky enough to own some property by a river, now this is my personal feeling about it. I would, and one of the trees fell in, I would leave it. And I'm going to explain why I would leave it. So one of the things in my bio, it mentioned that I did some snorkeling surveys in Missouri. And when I was doing that, it's very interesting because when you snorkel, you can actually see the diversity and see these different substrate types forming, the flow of the water, and how the fish and everybody's interacting with one another. And what happens when you get logs in the river, and I tried to mention this with the large woody debris, is that they create very diverse set of habitats. So that water's going to flow over it, and it's going to like put in a little scour, and then you're going to get deposition over here, and you're going to get maybe some large rocks here, some small, sediment here, and that diversity of the environment will allow then the diversity in the biology. So you get these different habitats that different types of species of fish are drawn to. And when you have more diverse habitat, you have more diverse fish species composition. So that's why I would leave it in, is because it creates that diversity that the different types of species are looking for various parts of their life cycle. It's not just species, but other species and their life cycle too. So.
Absolutely. All right. Another tree-related question. In the past decade, we've seen a huge loss of ash trees due to the emerald ash borer. Along rivers, this causes a large reduction in shaded waters in some places. How do changes in tree canopy like this affect river health?
Yeah, We typically talk about tree shading and river shading when it refers to trout streams. So trout streams can be very sensitive to solar radiation and heating from the sun, and consequently, when the tree canopy is removed and you get all this sun, you get increases in temperature, increases in algae production, all this kind of stuff in trout streams that are detrimental because the fish really like it cold. In warm water streams or cool water streams, you might get increases in algae production, but when the tree canopy is removed where there's not temperature sensitive habitats, other than them falling into the river and creating more habitat, just increasing the sunshine is not a big deal for most fish species. So yes and no. When they fall into the stream, they create, of course, habitat for invertebrates too, but just having more sunlight is not really detrimental to warm water riverine communities.
Yeah, I mean, the only other thing I could think is potentially like you could get more algae growth, because we see that in the springtime, right? Before trees will leaf out, you'll see,
Sure.
Some algae growth. But then once, the summer takes off and things start grazing on it and the shade comes in, that kind of changes. So maybe there would be a small change there from a biological standpoint, depending
And there are fish species that are equivalent to the herbivores grazing the algae. So you might get an increase in the number of those fish species, but because there's more food there.
Exactly. Yeah. All right. Well, here's a question about erosion. First, they thank you for your presentation and all the work you're doing. And then they ask, since natural river processes result in erosion, I'm wondering what your thoughts are about distinguishing between erosion that's more natural versus identifying areas that are caused by human disturbance.
Yeah, I'm glad someone asked this question because I really didn't have time to get into that. So a natural erosion, and it's all about degree. So erosion is erosion, but it's about degree. So natural erosion, you would expect lateral movement, kind of like those videos, of an inch or two lateral movement a year, maybe a little bit more. But if we have a stream that's out of balance, kind of like those images where there's a lot of erosion, a lot of calving off of the banks, I mean, we're talking feet plus a year. So it's all about degree. And when you're out of balance, then you can have a huge amount of erosion versus a stream that's in balance, where it's essentially the same amount of erosion. The erosion is the same amount of deposition. And so it's level with one another. But yeah, no, and like I said, it's a very difficult thing to figure out, is when you have too much of one, you're like, okay, what's going on here? Why is this happening? And it's typically has to do with what's going on in the landscape and what kinds of things humans have done.
Yeah, right. Absolutely. All right. I want to remind everyone that the Q&As are open. If you have questions for Janice about rivers and streams and how they behave, feel free to type those in there. And also remember, she does have her email address up there on the screen right now. So if there's a question you want to, engage with her offline, you can certainly think of doing that as well. All right, as we continue through the list of questions, here's one from someone who is involved with our volunteer stream monitoring program. And so they're familiar with collecting invertebrates as an indication of stream health. And they're curious to know, can the invertebrates that we collect give us a indication of the habitat quality, the physical habitat in a stream, versus what we traditionally think about as invertebrates are indicators of like pollution and water quality problems?
Very much so, and that's why you typically collect them in your surveys. So insects are one of the most diverse phylum on the planet. There's a whole bunch of them, and that diversity also is reflected in riverine ecosystems. And consequently, you can tell sometimes by what species you collect what exact habitat it is found in. So, like midges, they tend to like slow moving habitats where the substrate's soft and kind of like those inside bends that I was referring to. Whereas like caddisfly larvae, And some of the ones that, caddisflies, they make their little houses on their backs. They actually are one of those filters. So they like fast moving water, and they like to sit in those riffles and actually physically filter out some of that water, some of the sediment that's in the water and the nutrients. And so consequently, if you look at the composition then of the invertebrates and the insects in the community, you can get an idea. If you got way too many midges, you're like, okay, there's a lot of deposition going on here. And consequently, the stream might have some imbalance, or I don't know if you can have too many caddisflies, but that indicates that there's a lot of good riffle, clean kind of water moving through the sediment, similar to what a caddisfly likes to live in.
Great. Absolutely. Absolutely. I know right now I just got an email from someone who sent some photos of stoneflies, adult stoneflies that are emerging along the stream near their house. One of those winter active insects that we don't really think about in streams, but not only are the larvae indicators of good water quality, the nymphs, it's fun to see the adults emerge, because many of the species are active in the wintertime where they don't have a lot of predators after them. So, we don't always think about stream bugs at this time of year, but they're out there doing their thing. All right, another monitoring question from one of our volunteers. Is it possible to monitor channel shape change or erosion in a stream? Are there ways to do that? And if so, are there any ways that are kind of volunteer-friendly ways of doing it?
Oh, yeah. I think one of the easiest ways to get an idea of how much lateral movement's going on in your channel is to get a piece of rebar, fairly long piece of rebar, and hammer it laterally here into the side of the bank, the outside bank that's eroding. And if you mark it before you hammer it into that bank, you can see then, measure every single year how much more stick is sticking out of that bank, and you can get an idea of how much lateral movement your channel is doing and how much erosion is happening on that outside bank. So no, that's a really good cheap way to monitor how much movement your channel is doing, and especially if you don't have satellite imagery that's really detailed.
Right. Great. Fun idea, right? Wish I had a creek in my backyard. I'd do that just to see what it's doing. All right. Another question from the homeowner's perspective. We talked a little bit about trees along the stream and managing those, but more generally, do you have suggestions for anyone who lives or has property along a stream or river, how they could, help protect the habitat in that stream?
Yeah. So first of all, I would be cognizant of when you have a rain event and how much of that kind of overland flow is happening. And typically it's increased when you decrease the amount of vegetation that's in the floodplain. And so that idea I had about the large riparian buffer strips, so having vegetation all year round that is not only tall, but has really good root structure. So a lot of the native plants do. And what that'll do is that'll hold that soil down. And if it gets up and is flowing across the land, it'll filter then that sediment and keep it on the land before it gets into the river channel. I think I'm not going to go into the other stuff I was going to talk about. So that would be one way. So essentially managing the on-land vegetation is what I would do if I was a property owner that was right next to a stream.
Mm-hmm, mm-hmm. Yeah, definitely good advice. I know when I worked for a watershed council before I was at MSU, we helped with that also by offering rain barrels for sale for folks, so they could capture the runoff from their roof, so it didn't just wash right into the river. And that was a really popular solution too. And people can use that for watering their gardens or whatever, and it didn't just end up washing right into the.
Now I live in the city, so this didn't immediately come to mind. But if you're in the country and you have a septic system, that is another place where your nutrients are coming from the septic system. They're going underground into that river. You could, now this is something that I saw on this old house. So they have these new septic systems that are essentially zero nutrient release. They take out a lot more nutrients because they have this internal filtering system and lots of bacteria. Anyway, they probably a little bit more expensive, but these essentially, net zero nutrient septic tanks would also be a way that you could restrict your impact on that river.
Wow, that sounds really like a positive development.
Yeah, it was pretty cool when I saw it. I was like,
Yeah.
one of those if I ever need one.
Right, yeah, because I think, originally septic systems weren't really designed for nutrient control. It was to keep pathogens
Yeah, this
out
one's,
physically.
if I remember correctly, it was something like 80% of the phosphorus is removed. And I forget how much nitrogen, but it was, it was a major amount.
Yeah. Oh, that's really cool. All right. Well, right now I just have one more question in the Q&A box. So I'm gonna pose that to you. And it's going back to the ditches and channelization, especially in agricultural areas. We have a lot of stream miles in Michigan that are designated drains, and they're managed as such to keep water off farm fields and that kind of thing. Are there, more nature-friendly ways to design or manage these ditches?
This is getting into sticky territory. Let's see. That's a very good question. I don't know that I have much advice. I mean, I'm sure if they decide to remove it from the drain system, then of course you could do all these different things to restore the natural flow. But when it's still on the drainage system, so yeah, you're going to essentially have kind of like that balance. So the managers are going to want to manage it for that high power scenario. That's the kind of scenario that they like because it cleans out the drain and keeps things nice and flowing off the land. As far as things you could do, so maybe one of the recommendations that doesn't necessarily impede flow would maybe be instructing some of those or constructing some of those in-channel filtering habitats like riffles. So you notice in that one picture, it doesn't sort substrate anymore. You don't get that riffle run pool complex that you would normally get. But if you artificially added riffles to your ditch drain complex, then it would only slightly impede the water, but it could still go over it. So that might be one way. And if you do it in such a way that it doesn't necessarily increase the riverbed, because that's really what they're concerned about, the drain managers. If you construct a really, really small riffle one that's kind of like in the bed of the river, then you get filtering and you don't necessarily increase the riverbed. So you just got to think on it some more, I think, just be really creative. That's one of the things I like about this job is being very creative about solutions.
Right, definitely. And your suggestion reminds me a little bit about some approach that I've learned about called two-stage ditches. Janice,
yes, two-stage ditches.
Yeah,
yes, I've heard about those.
Yeah, one of the things with those is that they are narrow at the bottom, but then they get wide. So as the ditch starts to fill up, it can spread out a little bit, and it doesn't, have so much energy. It kind of slows them down.
Yeah, I guess in some way that might be helpful. I guess I'm not a big fan of two-stage ditches. Namely, I think they're trying to get at that idea of giving rivers room. Mm-hmm. But when they construct a trapezoidal channel, even a slight floodplain kind of channel, they're giving them room, but they're still constricting them. So it helps a little bit, but I'm not sure how much it helps. So yes, it might be a slight improvement, but does it really increase the functionality of that floodplain and the channel habitat per se? So right. Yeah.
Depends on what your goals are, right? Like what your goal is. If it's just to kind of slow that flow, then yeah. But if you're thinking about the stream as a system, as an ecosystem, then
maybe not so much function.
All right. Well, you know what, Janice, we had one other question sneak in. So if you don't mind, we've got a minute or so left. I'm going to ask this final question. When a dam is removed, lots of heavy equipment is used and driven in the river. how long can it typically take to recover fish habitat and population, if it ever does, after that level of disturbance?
Well, it's interesting that you bring up level of disturbance. Riverine fishes have evolved with high levels of disturbance. So if you remember those videos, that channel's moving back and forth all the time. So that's one of the reasons why having really lateral and longitudinal connectivity is so those fishes are moving around, and there's a disturbance over here, we'll just move downstream for a little while, that kind of thing. So when you remove a dam, and they've done some studies on this to see how quickly fish actually pass it and go upstream. And it literally is as soon as the water's pathway is open, those fish are moving. So as far as disturbance, yes, to us, it looks like things are disturbed, but to fish, as long as they can get through it. Now, the important thing about removing dams is to make sure that the resulting riffle that's left behind has low enough velocities that it can pass any size of fish. That typically is the problem. If we make it too steep and the riffle's too fast, then only the big fish are getting upstream, not the little guys. And consequently, we need to pay attention to that. But as far as disturbance is concerned, if you think about how these fish evolved in the environment they evolved in, relative to fish disturbance, it's not that great.
All right. Well, that's good news. All right. Thank you so much, Janice. I want to tell you how much I appreciated this. I see a lot of, comments of praise in the chat and thanking you for this presentation. And I want to echo that. I want to remind folks this was recorded, so the video will be posted in about a week on the MyCore website. Please check it out if you're interested. And I also want to invite you to attend our remaining 2 webinars in the series, including next week, next Monday, same time, same place. We'll hear from Jake Sawecki on aquatic food webs, specifically how do fish decide what to eat and why. So we hope we'll see you there. Thanks, everyone. Have a great afternoon.
Yeah, thank you all.